In the vast, silent expanse of the cosmos, a force of unimaginable power lurks. It's a beam of pure, concentrated energy, a celestial sniper shot capable of sterilizing an entire galaxy in the blink of an eye. We're talking about gamma-ray bursts, or GRBs. These are the most powerful and luminous explosions known in the universe, second only to the Big Bang itself. Imagine all the energy our sun will produce over its entire 10 billion year lifespan. Now, picture all of that energy being released in a matter of seconds. That is the sheer, mind-boggling scale of a gamma-ray burst. These cosmic phenomena are not just distant fireworks, they are a fundamental part of the universe's life cycle. They are born from the most extreme events imaginable, and their consequences can reshape the fate of entire star systems. So, what exactly triggers these cosmic cannons? What causes a gamma-ray burst to fire? The truth is, there are two primary culprits behind these cataclysmic events, leading to two different types of GRBs, short-duration and long-duration bursts. Let's start with the long-duration bursts, which last anywhere from 2 seconds to several minutes. These are thought to originate from the death of truly colossal stars, stars that are dozens, even hundreds of times more massive than our own sun. As these stellar behemoths exhaust their nuclear fuel, their cores collapse under their own immense gravity. This collapse doesn't happen quietly, it triggers a hypernova, an explosion so powerful it makes a regular supernova look like a tiny sparkler. During this core collapse, the star's material falls inward at nearly the speed of light, forming a rapidly spinning black hole at its center. This newly born black hole is voracious, and it begins to devour the surrounding stellar material, creating a swirling accretion disk of superheated plasma. The intense magnetic fields and extreme conditions within this disk then launch two incredibly powerful, tightly focused jets of particles and energy. These jets blast their way out from the poles of the dying star at over 99% the speed of light. When one of these jets happens to be pointed directly at Earth, we detect it as a long-duration gamma-ray burst. It's a fleeting but overwhelmingly bright flash of the highest energy light in the universe. Then there are the short-duration GRBs, which are even more fleeting, lasting less than 2 seconds. For a long time, their origin was a profound mystery. We now believe they are the result of an even more spectacular cosmic collision, the merger of two neutron stars. Neutron stars are the incredibly dense remnants of massive stars that weren't quite big enough to become black holes. They pack more mass than our sun into a sphere just a few miles across. A single teaspoon of neutron star material would weigh billions of tons. When two such objects are locked in a binary system, they spiral closer and closer over millions of years, drawn together by their powerful gravity. Their final moments are a frantic, violent dance that culminates in a cataclysmic merger. This collision unleashes a tremendous amount of energy, forging heavy elements like gold and platinum, and blasting out a short, intense burst of gamma rays. It's one of the most energetic events the universe has to offer, a true cosmic smash-up. So, we have these universe-altering explosions happening all the time. The question then becomes, have they ever affected us here on Earth? Has our planet ever been in the crosshairs of one of these cosmic sniper shots? Some scientists believe the answer is a chilling yes. They point to one of the major extinction events in Earth's history, the Ordovician-Silurian extinction, which occurred about 445 million years ago. During this period, around 85% of all marine species vanished from the planet. It was a devastating blow to life, and its cause has long been debated. The leading theory has often been a period of intense glaciation and a subsequent rapid warming. But what could have triggered such a dramatic climate shift so suddenly? A nearby gamma-ray burst is a compelling and terrifying candidate. If a GRB from a few thousand light-years away had struck Earth, its effects would have been catastrophic. The initial blast of gamma and X-rays would have stripped away a significant portion of our planet's ozone layer. Without this protective shield, harmful ultraviolet radiation from our own sun would have flooded the surface. This intense UV radiation would have been devastating for surface-dwelling organisms and marine life in the upper layers of the ocean, especially plankton, which formed the base of the food chain. This could explain the massive die-off of marine species. But the damage wouldn't stop there. The gamma rays would have also interacted with nitrogen and oxygen molecules in the atmosphere, creating nitrogen oxides. These compounds would have then formed a thick, reddish-brown smog, blocking out sunlight and causing a rapid global cooling, a cosmic winter. This sudden plunge in temperatures could have triggered the massive glaciation event that characterizes the Ordovician extinction. After the initial smog cleared, the depleted ozone layer would have remained, allowing the sun's radiation to bake the planet, leading to the rapid warming that followed the Ice Age. The sequence of events, a sudden mass extinction, followed by glaciation, and then rapid warming, fits the potential signature of a GRB impact remarkably well. While we don't have definitive proof, it remains a powerful and sobering possibility. This naturally leads us to the most pressing question of all: are we in danger now? Is there a gamma-ray burst with Earth's name on it, waiting to fire? The good news is that the odds are very, very low. For a GRB to be a threat, several things need to happen. First, the progenitor star or neutron star system must be relatively close to us, within our own Milky Way galaxy. Second, and most importantly, the jet of energy must be aimed directly at us. These jets are incredibly narrow, like the beam of a laser pointer. The chances of Earth being perfectly aligned with one are astronomically small. Most GRBs we detect are from billions of light years away, in distant galaxies. Their energy has traveled across the cosmos for eons, and by the time it reaches us, it is far too diluted to cause any harm. It's merely a whisper of a distant cataclysm. Within our own galaxy, potential candidates for long-duration GRBs, like the massive star Eta Carinae, are not oriented correctly to point their jets at us. And while neutron star mergers are chaotic, the sheer vastness of space makes a direct hit from a nearby event extraordinarily unlikely. Statistically, a life-threatening GRB event is expected to occur in our galactic neighborhood only once every few 100 million years. So, while the threat is real, it is not something that should keep you up at night. There are far more immediate and probable dangers facing our civilization. But the study of gamma-ray bursts serves as a profound reminder of our place in the cosmos. It shows us that the universe is not a gentle, static backdrop. It is a dynamic, and at times, incredibly violent place, operating on scales of power we can barely comprehend. From the fiery death of a single star can come a force that sterilizes worlds and reshapes galaxies. It's a testament to the interconnected and often destructive nature of the cosmos. Understanding these events doesn't just satisfy our curiosity, it gives us a deeper appreciation for the fragile and precious nature of our own world, a tiny, life-filled oasis in the vast and powerful cosmic ocean. Thank you for joining us on this journey through the universe's most powerful explosions. If you enjoyed this exploration of cosmic phenomena, be sure to subscribe to Space Repo for more deep dives into the wonders and dangers of space.